Hello students. In last lecture we discussed about the applications of the dipole, say axial line and the equatorial line. Now today we will discuss about the torque produced in a dipole when it is placed in a uniform electric field. Okay, so the topic is torque produced in a dipole when it is placed in a uniform electric field. Okay, so for now, let these are the electric field lines. So these are the electric field lines. Direction of electric field lines are from positive charge to negative charge. Let positive charge lie here and negative here. We are keeping one dipole, that is AB. This is the center. Here we will be having plus Q and here we will be having minus Q, or you can take in opposite, minus Q and plus Q. And let 2A be the length of the dipole. This is the angle of dipole making with electric field line. Because negative charge is present here and positive charge is present over here, so this positive charge will repel this one, this end in this direction. So force will exert on this point. So F is given by Q into E. This is F1. In similar manner, this charge will experience a repulsive force due to the presence of the negative charge in this direction. F2, that is Q into E. Okay. You can take minus QE. Minus QE means the direction is opposite to the direction of this force. Now, due to the pair of these forces, these couple of forces try to rotate the dipole in this way. Okay, so this is the rotation of dipole within the electric field. So this rotation is known as torque, and torque is produced due to the couple of force. So when any dipole is placed inside the uniform electric field, then both the ends of dipole will experience a couple of force. That is F1 and F2. Due to this couple of force, dipole torque will produce and dipole start rotating. Okay, so now this is rotating in this direction. This is the perpendicular distance BC, this is 2A and this is theta. So torque is given by, what is the formula of torque? Torque is given by force into perpendicular distance. Torque is equals to F, either F1 you can take or F2. So magnitude into perpendicular distance is BC, because this is angle, so this side will be our perpendicular. So force into BC. Now what is the value of F? F is given by Q into E. Into BC, we have the value of AB only, but we do not have any value of BC. But we can convert this BC in term of AB. So this is perpendicular, this is hypotenuse. I am writing it here. In triangle ABC, perpendicular and hypotenuse gives sine theta. Sine theta is given by perpendicular over hypotenuse. We want BC, so BC is equals to AB into sine theta. AB is what? 2A into sine theta. This with the value of BC. So we can put it here. BC is equals to 2A sine theta. Now we know that 2A and Q gives us dipole moment. So E into P into sine theta. So here torque equals to P E sine theta, or we can rewrite it as P cross E, because when we eliminate this cross product, then we will get sine theta. So this be the torque produced in a dipole when it is placed inside an electric field. Right? We can take one special case here. For the maximum torque and for the minimum torque. When theta is 90 degree, means if our dipole is placed like this in the direction perpendicular to the direction of electric field lines, so then torque is given by P E sine 90, and sine 90 gives us 1, so it will be P into E. So that will be maximum torque. Second case, when theta is equals to 0 degree. This is the angle like this, 0 degree. So in that case angle will be 0, so torque will be P E sine 0, and sine 0 gives us 0, so it will be 0. So minimum. So these were the two special cases for the torque produced in a dipole when it is placed in electric field. Okay. Next article depends on the same thing, same result, and article is the potential energy of a dipole when it is placed in a uniform electric field. Potential energy of a dipole when it is placed inside electric field. The same diagram we need to draw. Let these are the electric field lines of external electric field, and this is the initial position of the dipole, theta, say theta 1, okay, plus q minus q. Now if this is the initial position and we want to change the position of the dipole within the electric field, we want this dipole in this way, or we want this dipole in this way. So in the both the condition, we need to do some work. We need to do some work to change the position or to change the angle of the dipole within the field. So that amount of work done is known as potential energy of the dipole. Let dipole is placed at angle theta 1 within the electric field. Okay, and suppose this be the second position that we want. Okay, this be the direction of change. Because force is acting in this direction and we need to change the direction in opposite way, so we have to do extra work done. Let dipole is placed at angle theta 1 within the electric field and we want to change the position of dipole. For this we have to do some work done. We have to do some work against the field, and that work done will store in term of its potential energy. Okay, so work done is given by dW. There is one formula, that is torque into d theta. Because we know that torque is given by PE sin theta. Okay, let me tell you why this formula comes, or the derivation of this formula. Since we know that we are changing the position of the dipole from AB to AB dash, let it be B dash. Okay, so there is a change in angle as d theta. So formula for angle is given by length of arc upon radius of arc. Okay, so what is the value of displacement here? So B dash is given by AB into d theta. AB is our 2A into d theta. And what is the formula for work done? Force into displacement. So force into displacement is B dash. For this, F is Q into E, B dash is 2A into d theta. So this gives us 2A into Q, P into E, okay, into d theta. But P is torque for the stable equilibrium. So torque into d theta, that is equals to dW. So that's why we wrote this formula directly. Now we can use the value. So dW is equals to torque is P into E sin theta for the general equation into d theta. But this is the small work done and we want the complete work done. For total work done, integrate both sides. Then we will get this one, P into E, I am keeping outside, sin theta into d theta, and we are changing the angle from theta 1 to theta 2. Integration of dw is w pe. Integration of sin theta is minus cos theta. Limit from theta 1 to theta 2. So we can put the limits cos theta 2 minus cos theta 1, right? This work done will store in term of its potential energy, which implies that U is equals to minus PE cos theta 2 minus cos theta 1. And there is one question, why potential energy is always negative? Because we have to do the work done in the direction opposite to the field, that's why. So this was the potential energy of a dipole when it is placed in the uniform electric field. Okay, there is one more thing. In the last topic we were having the formula for torque, that was torque equals to P into E into sine theta, and we were having two cases. When theta was 0 degree, then torque is equals to PE sine 0, it means 0. So for this case, that is known as stable equilibrium. And when theta is equals to 180 degree, then also torque is equals to PE into sine 180, that gives us 0, but this time it will be unstable equilibrium, because it depends on the charge, whether it is positive in front of the positive part or negative in front of the positive part. Okay, so these are the 2 points. For uniform distribution, torque is given by P into E, right? But what about non-uniform? Of E, then torque will be P into E into R. What is R? R is the position vector of non-uniform field, right? This will be the result for the non-uniform distribution of electric field.